So, dare I ask how things are going with homework?
It's all right.
Okay.
Wish I were a little bit further along.
Mm-hmm.
Really like to turn them in on the deadline, but I just got a lot of stuff. So,
Also puts you well ahead of the rest of the class.
but doing it on the deadline gives me the time to review stupid answers.
Okay. Well, I mean, homework, I'm behind because I have homework treaties that I still need to grade, and that's certainly on the docket for this week. So, no one's asking questions at this time? Any problems? What?
Question 9.
Wait. Sorry.
Example 9. Question 9 on your homework.
Question 9.
Yeah.
Oh, okay. Yeah, so I was asked about that by Vivian earlier. It's a strange, yeah, it's kind of a strange problem because on one hand, like it tells you, yeah, derive this equation from this one, and then you go look there and it says that says the detail of this are asked in problem 9. But problem 9 is very narrow. It only says show that this equation follows from this one. Don't do anything else. Now, one thing, and they mentioned integration by parts. So, okay. So, what I will do is I'm going to write down 2 properties that would hold for inner products in general of functions. And these will help you work out this problem. Okay. So, okay. So inner product fun facts. Now, first one is, suppose you have an inner product of this form. So, product of 2 functions, f of g, f of t, g of t, and then with a third one function, h of t. Okay. So, the thing is, if we write out what that is, and based on the book's definition of inner product, h of t has to be conjugated. But what happens is all of these are multiplied. Well, we'll just use the fact that multiplication is commutative and associative. I can move things around within this product. So I could do this. I could take the, that's weird, the chalk is like deciding not to work. I can associate G with H instead of F. Well, that has to be conjugated. Okay. So I could think of it this way, where I'll put a conjugate over the whole thing as long as I also put 1 over G. So effectively that one is undone. So the result would be inner product of F with G conjugate H. So now, and of course, if G is real, then one argument to the other. So you can shift things around like that. So there's at least one place in this problem where you need to do that to get it into the. So you can take advantage of the niceness of multiplication. Okay. The other fun fact is if you have a derivative, inner product of something else, then using integration by parts, you're allowed to move a different from one function to the other with this consequence that you get a minus sign. Okay. Provided that, let's see, f of t g of t with limits a and b is 0. So in other words, the boundary terms from integration of parts end up going away. And so really, what we have here, this is literally integral of u dv is equal to that, which is 0, minus integral of v du. So there's integration by parts in inner product form. So this comes up in a problem also where you have to shift a differentiation operator from one argument to another. Terms in the expression that you're working with. So it might be a good idea to just expand things out, work with things separately, and then put them back together to get them in the format you want. Because when you have an integral with multiple terms, it's tempting to just like, oh, I pick an integration strategy and apply it across the board. And you can't, a lot of times it doesn't work. You need to use a different technique on one term than another. Okay. So with these tools, you can make this work. Okay. So give it a shot. Right. Any other? Okay. Well, in that case, let's get through these 3 pages of notes. Because now we're getting into something completely different for the remainder of the course, and that is wavelets. Okay.
And our Haar wavelet analysis.
What?
Our Haar wavelet analysis.
Yep. And multi-resolution analysis in general. Unfortunately, it looks like we're going to run out of time to look at the Adobe sheets.
Oh, that's too bad.
Yeah. Well, the 3-hour midterm will do that. Like Gilligan's Island. 3-hour tour. It probably felt like a shipwreck, too.
I never thought that Gilligan's Island could properly be associated with math tests. It just shows that there are homeomorphisms from the strangest thing.
Yep. Okay. All right. So, and actually, this is meant to be sections 4.1 and 4.2, but really 4.2. 4.1 just poses the question, why wavelets? And fortunately, there's a simple answer. Because suppose you have a signal that behaves like this, like it's 0 for a while, and then all of a sudden it becomes non-zero, highly oscillatory, and maybe it goes back down to 0. Now, the tool that we have for studying signals so far is a Fourier transform.
Yeah.
So you can go ahead and say this function f of t, and it's sampled at various times, and then you can take like the discrete Fourier transform of that. Now, that will give you a frequency content of a function, but these jumps, like the location of these jumps, so when they occur in a signal, cannot be detected by Fourier transform. Because what you have for Fourier transform is, for each frequency in the signal's bandwidth, you have an amplitude. Those numbers tell you nothing about when things happen. So you get frequency information from the whole span of the signal over the entire time domain. You don't get locality. There's no indication about when features happen. So you get frequency information, but not time information. Now, one alternative that people use is the short time or windowed Fourier transform, where you focus on a particular subinterval in time. Like maybe you cut your domain up into equal space subintervals of equal width and do the Fourier transform on each one. So, for instance, if I divvy this up, then on each of these pieces I'd have 0. So I can see, okay, nothing's happened yet, and then in here something's happened. But that's not very flexible. It only narrows it down. It doesn't really give a precise information about when things happen. So we want to try something completely different that can give us locality in physical space, which for signals it refers to a time variable, and in frequency space. So wavelets are going to help us do that. All right. So the first thing I'm going to define, we're going to look at Haar wavelets. But before we can introduce the Haar wavelets, you need something more basic than the Haar scaling function. And thankfully, very easy function to work with. So I'm going to use phi to refer to the scaling function, and it says it's equal to 1 on the interval 0 to 1, or, okay, up to but not including 1, whatever, and then 0 otherwise. So it just behaves like this. So not continuous, unfortunately. It'd be nice to have wavelets that are continuous, and there are families of wavelets that have nicer properties, but they have more complicated formulas. But this is a good starter wavelet, if you will. Okay. So, okay. So what I can do is take this function and take translations of it. So this is non-zero on an interval of width 1. So if I take translations of this function, where unit translation is always an integer, then what I can define are, I can use this to describe piecewise constant functions, where the pieces, where the discontinuities can only happen at the integers. Okay. So now I want to work with those kinds of functions. So I'm going to find V naught to be the space of all functions of this form, where you have linear combinations of your Haar scaling function shifted by k units, where k is an integer. And we have our coefficients being real numbers. Now, one condition I'm going to attach to this is that we're only interested in functions of this form that have a finite number of non-zero terms. So the 8k can be any real numbers, except only finitely many of them can be non-zero. So in other words, with finite support. Support referring to the portion of a domain in which a function is non-zero. Okay. So it's a technicality that I'll include up front here and then probably gloss over in the future, but I'm on the record with it because I don't want to write every single time. Okay, so as an example, find a function f and v naught in terms of these shifted phi functions. So 2 phi of x plus 3 phi x minus 1 plus 3 phi x minus 2 plus or minus 5x minus 3. So this is a piecewise constant function, and the function values are basically given away by the coefficients. So we jump up to 2, then up to 3, stay at 3, then jump down to -1, and then back up to 0. So the graph behaves like this. So we have discontinuities at 0, 1, 3, and 4. So at those 4 x values, we have discontinuities. Now, so we have one graph transformation. I guess you got to teach about graph transformations, don't you? In 101? Okay. So.
Yeah, but topology does just a much better job with it.
Let's not go there. One of the things, I never took a topology class. And there are some people in this department who consider topology to be like one of the fundamental areas of math. And like, everyone should have it. I was like, well, I kind of missed that boat. So we haven't offered it in quite some time.
I wish that we would.
Yeah. Well, and sometimes I picked up a topology book and started looking at it, but my eyes glaze over. It's like,
Everybody has their own interests. It's just.
oh yeah, yeah.
It's just there's a different. It's one of those things that, yeah, people can survive without it. Just like no, to be fair, just like there's any field where not everybody's going to love every area of mathematics, and if they do, they're not going to accomplish anything because they'll be drawn too thin.
Yeah. Yep.
But it's one of those things that someone can feel really naked without it.
Yeah. Yep.
Speaking of one of those people that feels somewhat naked without it.
Okay. Yep.
Definitely a plug for it.
Yep. Okay. So that's one graph transformation. So another graph transformation is either stretching or compressing the graph horizontally. So replacing x with, in our case, work with powers of 2 times x for convenience. Okay. Now, so I can define a related space V1 be the space of functions of this form, again with finite support. It's not going to write this every time. The coefficients times phi of 2x minus k. Where k is any of the integers. So, again, piecewise constant functions, but now the discontinuities occur at the half integers. So as an example, I'll let f be 4, 5, 2x plus 2 phi of 2x minus 1 plus 2 phi of 2x minus 2 plus minus phi of 2x minus 3. So this belongs to V1. So this has discontinuities at x equal to, 0, because it jumps up to 4. But then, at x equal to 1/2, it's going to jump down to 2. And then this piece will be enforced from 1/2 up to 1. But then the coefficients are the same, so there's no discontinuity here until we get to the end of where this function is non-zero. So this starts at x equal 1 up to 3/2. So So 3 half squares of discontinuity when this piece takes effect, up until where, look at where 2x minus 3 is equal to 1. You solve that, and you get x equal 2. So that's the last place where it was discontinuity. Then it'll go down to 0 and stay there. So V1 describes piecewise constant functions that can have discontinuities at the half integers, which can include the integers also. So there's a wider set of possible jumps. Okay. So any questions about how these functions behave? So really, finding out where we're discontinuities, but looking at where's the argument equal to 0 or 1. So I can set this equal to 0 and 1 to find out where the interval begins or ends. And then see where coefficients match or don't match to find out if there's a discontinuity. Okay. Now that we have V0 and V1, of course, mathematicians always love to generalize.
Well, that's kind of the profession, isn't it?
Yeah. Okay. Well, you take ordinary multiplication and try to figure out, okay, let's apply this in as many other contexts as we can think of, and then you have a modern algebra class.
And then people invent things like non-associative groups.
Oh, yeah.
Non-commutative makes sense, but non-associative.
Can you even call it a group then?
You can call it group. Okay, set. Yeah, to be fair, it's a set. That is a misnomer. See, but that's what comes from just auditing classes instead of taking. I wouldn't have made that error otherwise.
Yeah.
You found discontinuities. You substitute. You make these numbers 2x minus 1 0.
Yeah.
Is it? So 2x minus 2 equals 0 is 1.
Yeah, the thing is, so like, where this is equal to 1 at x equals 1, whereas where this piece ends, and where this piece begins also at x equal 1. But notice the coefficients are the same. So where these are equal to 0, 1 is where discontinuity might occur. But to be sure, you look at the coefficients. So when you have consecutive pieces like that, where there's a matching coefficient, there's no discontinuity in between.
Okay.
Yeah. Same with this function, because it did this. It could have jumped here, just chose not to. Okay, so Vj would be the span of functions of this form. So Haar scaling function of 2 to the jx minus n, where n is an integer. With the limitation that, again, finite support is expected. So any sum of coefficients times these functions. Okay. So the function is in Vj. F has possible discontinuities. At x is equal to an integer divided by 2 to the j. So we saw at V0, discontinuities can only happen at the integers. For V1, they can only happen at the half integers, and so on. And because functions in all these spaces are piecewise constant, which is a limitation on wherever discontinuities can be, that tells us that V0 is contained within v1, v2, and so on. Because v1 functions in v1 can have discontinuities at all the points where functions of v0 can have them, and more. Each new space is adding more points of possible discontinuity. And it's a strict inclusion because of new discontinuity points being added. Okay. So the nice thing about this is, as your resolution increases, in other words, as J increases, you're looking at functions of a finer and finer resolution, at least no information is ever lost. Okay. So whatever jumps you have here get preserved in the next space and the next. Okay. Now, as a consequence of how these spaces relate to one another, we have these properties. So a function is in V0 if and only if you dilate the function, so you multiply x by 2 to the j, so that's going to, well actually it's the opposite of dilation, it's going to contract, so it's an undilation. Must be in Vj. And then the second statement, which is actually not all that interesting in light of the first, function is in Vj if and only if f of 2 to the minus jx is in V0. So, really you're just multiplying the argument in both cases by 2 to the minus j to get this. To give you an idea as to how the proof works, so I'll call this a partial proof. It's actually not very interesting. So suppose f of x is a sum of Haar scaling functions in the form x minus k, because it's in V0, so it's just a sum of integer translations of 5x. Then, I just replace x with 2 to the jx. So I get some ak phi of 2 to the jx minus k. But that's the very definition of a function in Vj. Right. So it's easy to move between these spaces just by multiplying your argument by positive or negative powers of 2. So if you multiply by positive power of 2, you go up this hierarchy, and then a negative power of 2, you go back down. Okay. Now, because the 5 functions have such a simple form, being piecewise constant, it's actually quite easy to obtain an orthonormal basis for one of these spaces Vj in terms of these 5 functions. But this property I just showed you is something that will come in handy a little later. Okay. All right, so theorem I'll prove is so this set where I take scaling factor 2 to the j over 2, and then times phi of 2 to the jx minus k, where k is an integer. normal basis. For Vj. Now, to prove this, I'd have to show that if I take the inner product of one of these with itself, I get 1. And if I get the inner product of one of these with a certain value of k and with a different value of k, that I'll get 0. So first, to show what we have for this is the same index. So I have inner product of 2j over 2. Or actually, I'll just look at the norm. So it's the L2 norm squared. So that would be the integral minus infinity to infinity of 2j over 2 phi of 2 to jx minus k squared. Well, the function is real, so I don't need to conjugate anything. So it's just the square. Okay. Now what I'll do is make a change of variable. So let y equal 2 to jx. This whole thing should be squared. Okay. So dy is equal to 2 to the j dx. Well, I have 2 to the j over 2 squared, which is 2 to the j. So 2 to the j dx is in there. It becomes dy. So now, and scaling x like this is not going to change the domain of integration. It's still going to be minus infinity to infinity. So I get minus infinity to infinity phi of y minus k squared dy, just from making the change of variable. Now, I'm going to make a second change of variable. Let z equal to y minus k, so dz equals dy. So it's just a translation. So same domain. So I get phi of z squared dz. But phi of z, the Haar scaling function's most basic form, it's only non-zero between 0 and 1. So that cuts my interval of integration 0, 1. But on 0, 1, phi is equal to 1. So I get 1. So each of these functions has a unit L2 norm. So that's one condition needed for orthonormality. Any questions about what happened here? Fun with few substitutions. That's pretty much all it was.
That's the kind of problem I want to see on the test.
Okay.
But no complicated computation. All it requires is understanding a little bit of calculus.
Well, the rest of this might be a better candidate for a final exam problem.
Well, I understand that. I wasn't thinking necessarily for this class.
Oh, okay.
I was more thinking, wouldn't that be awesome on a Calc 1 or Calc 2?
Oh, I see. Oh, yeah.
Because it equals 1, and so frequently we have for the kids, and they're not really all that confident. We have these awful answers that just look disgusting.
Oh, like in the online homework and stuff?
Yeah, and it's just like,
You know,
wouldn't it be nice if we had problems for them?
that's one of the regrets I have about, like I teach 102 online. I use Hawk's Learning. And so we have a lot of word problems, and sometimes the correct answer turns out to be like 8 digits long. And so it's funny, it is kind of comical when the correct answer is like 80,573,264, and then the student fills in 2. And
Yeah, that definitely off by several orders of magnitude.
yeah. So it's like something went really wrong. But yeah, if they can make things work out a little more nicely,
Yeah.
so students can see we're on the right track.
I don't know. I've just run into so many students that just make a computational error, and it's like, I don't understand this. And,
Yeah.
you know, this,
Yeah, and
anybody can switch a sign.
also, it's nicer is more opportunities for partial credit. But when the student only gets to enter the final answer, a very long process, because sometimes like my last class might break your problem down a little more, and maybe there should be a little bit more of that. So that way, weaknesses can be pinpointed and things like that. But on the other hand, sometimes I've given very elaborate problems in classes like calculus, whatever, and after so much manipulation and computation, the final answer turns out to be the correct answer turns out to be like 0 or 1 or something like that, and the students get outraged. Like, 1? I did all that work to get 1? Like, shut up. Didn't even know you got it right.
It's hard to get problems like that.
Yeah, and then there is a certain pride to be able to construct them. Actually, I wonder if I can find it easily. I'm hoping I can show you my favorite example. So I remember what class it was for, so that will help. And I think I know what assignment it was for. Okay. Whoops. Oh, it's not that one. Maybe the next one. Oh, yeah, I found it. Okay, so yeah, so this funny problem was given fx piecewise defined, be okay 5. I have to write it carefully. X squared plus 25. Okay, minus. Okay, for x non-negative, and then for x negative, almost the same thing. Oh, okay. Actually, it's exactly the same thing except a minus. So, I'm not gonna write it again. Minus all that. Yeah, it's one thing we're doing copy and paste in LaTeX, but
Slightly harder on a board.
yeah, and so, and the problem was very simple to state. Compute f prime of 0. And I gave them two options. Either they could apply differentiation rules, or they could, this is for Cal 1 class, or they could use a definition of a derivative in terms of a limit. However, I explained to them that no matter which approach they use, they had, because the function is piecewise defined, they had to apply that chosen approach for both pieces, and they had to make sure they agreed, because otherwise the derivative doesn't exist at 0. And yeah, the answer turned out to be 1, and some students were upset about that. They thought that their hard work should be rewarded with a more elaborate answer. I don't understand their thinking, but yeah. And Kirby, I've only taught Cal 1 at USM once, and I didn't think of giving him this problem. So if I ever teach Cal 1 again, well, I could give it to 102 students. They take derivatives, but they'd probably kill me.
Definition of zero, like definition of derivative will easy for this one, isn't it?
Well, I asked in the comments, like, which approach would be easier.
Both
Yeah.
h plus 0 plus h
Yeah,
cancel out.
and-
So
And I believe it would be easier. And I think what I was trying to trick the students because they're so tempted to use differentiation rules and everything,
yeah,
but that'd be kind of a mess with this one.
yeah.
Yeah.
That's good.
So. Yeah. So that was interesting. Okay. Well, if you want to do it again, but not now. Okay. Now, okay, I have to complete this proof. So, okay. Well, not before I take a picture of this. Okay. So now I have to work with translates of this function for different values of k and show you get orthogonality. So let m not equal to n. So the inner product of 2 to the, okay, it really should be m over 2 phi of, oh wait, no, still j, x minus m, with 2 to the j over 2 phi of 2jx minus n. So now I'm going to integrate the product of these from minus infinity to infinity. So you get 2 to the j for multiplying those together. Phi 2 to the j x minus m, phi 2 to the j x minus n. And I do the same change of variable as before, at least the first one. So I let y equal 2 to the jx, so dy is 2 to the j dx. So the 2 to the j gets swallowed up by the change of variable and absorbed into the dy. So now I have phi y minus m, phi y minus n dy. And I could do one more change of variable as a shift. So z is y minus m. So dz equals dy. So I have phi of z and phi of, so I write this as y minus m plus m minus n. So z plus m minus n dz. Now, this is non-zero on 0 to 1. And this is non-zero on m minus n up to m minus n plus 1. Now, in order for this inner product to be non-zero, these intervals must at least overlap. Well, the endpoints are integers, so they actually consecutive integers. So not only must they overlap, they must coincide. The only way they can coincide is if m is equal to n. This must be 0. But m is specifically assumed not equal to n. Therefore, 0. So that completes the proof. So we have orthonormal basis of these functions for Vj. Any questions about what happened here? Okay. Oh, almost proved 2 pages. Okay. Now, what I'm going to do is, from the scaling function, now that we have some understanding of its properties, I can define the first actual wavelet, the Haar wavelet, in terms of the Haar scaling function. So I'm going to use a Greek letter psi to denote the wavelet as opposed to phi for a scaling function. And it's going to be phi of 2x minus phi 2x minus 1. Now, this formula is by itself not very illuminating. It's much nicer to see a graph. So if I were to, so phi of 2x is this function that is equal to 1 only from 0 to 1 half, and 0 otherwise. Now, phi of 2x minus 1, if I were to rewrite this as phi of 2 times x minus 1 half, then, yes, it's a translation of phi of 2x by half a unit to the right. And it's negated, so it just looks like this. Okay. So here we have minus phi 2x minus 1. So now we put them together, and so this is psi of x. So it's positive on the first half of the interval, 0 to 1, and negative on the second half. Okay. All right. Now, if you were to compare this to the scaling function that's equal to 1 on the entire interval from 0 to 1, you would see that the scaling function and the wavelet are orthogonal to each other, because we'd have positive area here with negative area here canceling it out. So if you're multiplying by scaling function, you're just going to get psi itself on 0 to 1. And the integral of that, you can see just geometrically, would be 0. Okay. And that's a kind of orthogonality that's going to be helpful to us in wavelet analysis. Okay. All right. Now, all right, so now let's suppose I consider a function in V1. So let's suppose that f is a recombination of functions of this form from V1, so 2x minus k. Now, so when is f orthogonal to V naught? And the way I can answer this question is most easily seen by examining graphs of functions from V1, where this function is, and V naught. Because a function like f can have some behavior like this. So each of these spaces would be like a half integer. 1/2, 1, 3/2, etc. Okay, and that's where we can have discontinuities. However, a function in V0 can only have discontinuities at the whole integers. So something like this, like constant along this whole interval, and then it can jump to something else. So a function from V0 is not allowed to change value at the half integers. It must remain constant across them. So what that means is, if I focus on an interval of this form, some integer k up to k plus 1. Now f is behaving, so here's k plus 1, and here we have k plus 1/2. Now your function from V0, so g, is constant. Your function from f is constant on each half. So, and from f and g, both, you're going to have a repetition of situations like this on every other interval that's bounded by consecutive integers. So what happens is the integral from k to k plus 1 of f with g. Now I'm going to assume that, now the thing is I can just use g, I don't have to conjugate because we're assuming from the beginning that everything is real. That would be equal to, I can factor out g of k. Why? Because it's constant on that interval. Second of all, I can actually say that, so let's suppose that this value is AK, this value is AK, well, actually you'll use, I'd be careful about this, AM and AM plus 1, based on however I number the terms. Okay, so those are the actual values of F on those half intervals. So this would be G of K, and then I'd have AM, so we have the height of AM and a width of 1/2, so AM over 2, plus AM plus 1 over 2. So that's the inner product after I've evaluated everything, because F is a constant function equal on each half interval. Each interval has a width of 1/2. Thus, very appropriate to call it a half interval. So the question is, when is this equal to 0? So this is 0 if and only if AM is equal to minus AM plus 1. Assuming that because AM corresponds to the first half, M must be an even integer. Actually, I want to make sure I get that right. Oh wait, K is 0. Yes. So what we have here is so each odd coefficient is equal to minus the preceding even coefficient. So that's not really the best way to express it, but I can answer this question in terms of this form of F. If A 2k plus 1 is equal to minus A 2k, where all integers k. So that's when f is orthogonal to every function in V naught, because you're going to have a cancellation. So this inner product would not be 0. But if I move this down to be minus this, then it would be. So when you have a cancellation, but then that means that f is behaving locally like this. But where do we see that graph? Right here. It behaves like a Haar wavelet on each subinterval bounded by integers. So what I can do is, so in that case, when f satisfies that condition, so I can say f is equal to, so I can just replace, I can have a2k phi of 2x minus 2k minus phi of 2x minus 2k minus 1. Because this term, this phi would normally be multiplied by a2k plus 1, but that's equal to minus a2k. But this fits the definition of a wavelet, the Haar wavelet. So we get psi of x minus k. Wait, 2x minus 2k minus 1. Yes, okay. So the functions in V1 that are orthogonal to V naught are the ones that can be written as a linear combination of translated wavelets. So now I'm going to work with those. So I can define W naught to be equal to sum of linear combinations, again, of finite divorce, blah, 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 of wavelets instead of scaling functions. Okay. So the V's are spans of scaling functions. The W's are spans of wavelets. Okay. So now I can make a similar definition. Wj is a set of linear combinations of dilated or really undilated wavelets. All right. So a nice theorem that we have is that Wj is the orthogonal complement of Vj within the space Vj plus 1. So if you consider Vj plus 1, which contains Vj, to be like your universal vector space, then these two are subspaces of it and are orthogonal complements of each other. Furthermore, so really, as a result of that, I can say Vj plus 1 is equal to the direct sum of Wj and Vj. So each space of scaling functions at a higher resolution is a unique linear combination of functions from a next level resolution down, combinations of scaling functions, and wavelets at that same resolution. You put them two together, you get the next level.
Okay. So the direct product ultimately defines Vj plus 1.
Yes.
Yes.
Okay. So if I were to take this to an extreme, I could say, like, for instance, Vj is equal to V naught, direct sum W naught, which is V1, direct sum W1, the free V's give me V2, and I can keep all the way up to W J minus 1. So, well, these are all direct sums, so I had to put them in circles too. Okay.
It was hard.
Oh, yeah. So, any function in Vj can be written as a unique linear combination of orthogonal functions, orthogonal to each other, one of them being at the lowest resolution, just combination of a scaling function, without any dilation, and then combination of wavelet functions at varying resolutions, starting from the lowest resolution up to the highest, same resolution as, or just stopping short of Vj. So that's the beginnings of multi-resolution analysis. That each of these, your pieces from each of these, describe increasing levels of detail.
And this, of course, makes many of the recursive algorithms that we have for all wavelengths possible.
Yeah. Okay. Now, as far as how you would prove this, it's actually more fun with substitutions. Let's see, how am I doing on time? Oh, actually, not too bad. Because, so this was actually one theorem, this line here, and then, okay, this is essentially the next theorem, although the final theorem, which I'm not going to prove, states not for Vj, but if you take Vj all the way to infinity, you get L2 of L2 of a whole real line.
Yeah.
And it's equal to this sum taken to infinity. Okay.
That makes sense.
Yeah, so you can. So it's a nice decomposition of.
This is just another example. If you really want to understand the world, really understand series.
Yeah. Yeah. So I could say that if f is in L2, f can be written as a combination f naught plus a sum of wj, where f naught is in v naught, each wj is in capital Wj. And this decomposition is unique because functions in these spaces or different spaces are orthogonal to one another. Okay. All right. Let's see. Yeah, I do want to show you why this works out. Using results I showed earlier. And then I think that'll be it. Well, yeah, I'll be out of notes. Actually, if you start running Wednesday's notes, that could be a problem. Okay.
I hope it will be fun.
Well, this is a partial proof. It'll be the interesting part of it. Okay. So, to show that Wj is equal to Vj orthogonal complement. Okay. So I'm going to let G be in Wj, and I'll let F be in Vj. And I want to show that F and G have to be orthogonal. Now, because G is in Wj, I can express it as a linear combination of wavelets. Okay, so I'll have some combination of aka psi of 2 to jx minus k. And then f, because it's in vj, that means that f of 2 to the minus jx belongs to v naught. Now, I already showed earlier that functions in v naught are orthogonal to functions in w naught. So from here I can say that the inner product of f with any linear combination, but for my specific linear combination, I'm going to choose the same coefficients, ak. But instead of putting these same wavelets, I'll put psi of just 2x minus k. All right. Oh wait, not 2x, just x. So translated wavelets. Okay. Oh, sorry, not f. 2 to the minus f of 2 to the minus jx. Has to be that form of f. Must be 0. And the reason why is this is in v naught. This is w naught. So I've already shown that v naught and w naught are orthogonal to each other. So I'm using it to show that vj and wj are orthogonal to each other too. Now, what is this? This is the integral, which I already know is equal to 0, of f of 2 to the minus jx sum psi of x minus k dx. So now what I'm going to do is make a change of variable like before. Y is 2 to the minus jx, so dy is 2 to the minus j dx. Or in other words, dx is equal to 2 to the j dy. So I'm going to get a factor of 2 to the j out front, same limits, and now I'll have f of y, and then I have 8k, so x is equal to 2 to the jy. But the thing is, now it matches the form of g. So I have 2 to j, inner product of f and g. We already know this inner product is equal to 0. But what I've done is use the fact that this seemingly pulled out of thin air integral is 0 to show that f and g must be orthogonal when f comes from vj and g comes from wj. So yes, the real conclusion here is wj is vj orthogonal complement. Okay. And the thing is, all these functions, and if you take wj and vj together, those make up all the functions in vj plus 1. So that's the space that you're taking your orthogonal complement within. Okay. There is more to the theorem, but how you would go about showing the rest of this is essentially the same as how I showed it earlier for the case of j equals 0. So showing that v1 breaks down into w naught direct sum v naught. So to do that for general j is not really interesting. Because basically you're making more changes of variable like this. Nothing to it. Something no student wants to hear.
Well, the problem is that being truly rational takes a lot of effort, even if one has begun to develop the habits necessary to being truly rational.
Yeah.
But when it makes sense, I mean, it really makes sense.
Yeah, definitely.
I mean, mathematics is pretty much the only profession where you could really know something. I mean, it's serious. I mean, all those poor physicists out there, they think they know something, and they're just taking samples, you know?
Yeah.
There are these anomalies floating out there that they just aren't accounting for, that some brilliant physicist 50 or 60 years down the road is going to come through and say, oh, those stupid people back then didn't understand anything about physics.
Yep.
But, you know, there's nobody in the world that will really overturn what Archimedes did.
Yeah. Yeah.
No one can.
Yeah. Well, as Paul Simon said, proof is the bottom line for everyone.
Yeah.
Okay, well, and I've come to the end of my notes. So.